Okay, now I'm talking about NOMU, Neural Optimization-Based Model Uncertainty, which is joint work with Jakob, Hanna Wutte, who just gave the previous talk, and our supervisors Sven Seuken and Josef Teichmann. So I start by explaining you what do you mean by model uncertainty, which is also called epistemic uncertainty. If I'm interested in a certain unknown function and I only observe it on a few data points and in between I don't have access to this function, I could just simply fit the neural network through these points to have an estimate which also gives me some predictions outside of these training samples. But of course, they also have some uncertainty because outside of the training data set, I don't really know what's happening. So this is why we developed this method NOMU, which gives us these uncertainty bounds that we think with a high probability the unknown function is within these bounds. So from a theoretical point, mathematically, this could be achieved by a Bayesian method, where you define a prior on function space, and once you observe some training data, you could mathematically define then there's a posterior of such uncertainty bounds. And Monte Carlo dropout is one of the examples which tries to approximate this posterior, and in theory, this posterior would make a lot of sense. But what we see here, that this approximation that they actually compute in practice, if you don't train it for 1,000,000 of epochs, but just 1,000 epochs, it is not a very good approximation, which is not a good approximation of the posterior. But with our method, we don't really exactly define a prior, but we have already quite a strong intuition how the posterior uncertainty bounds should look like. So we made a method which just directly obtains such uncertainty bounds. Okay, so how should they look like? So first, trivially, uncertainty should always be non-negative. Then at the training data points, we want the uncertainty to be close to 0, because at the training data points, we know already what happens, so we have no uncertainty left. So here we're always in the noiseless setting. And what we see here, for example, for Monte Carlo dropout, that it does not fulfill it. Also at training data points, when we told the method that there's no noise, it has still a lot of uncertainty. Okay, then the further we move away from the training data points, the more uncertain we should get. And then D4 is maybe more interesting, that this metric for distance that we use in D3, this should also be learned from the data. Like for this data set here on the left-hand side, there nothing really happens. So a little distance is not so meaningful, but here on the right-hand side, even if there's just a little deviation in the x direction, you should have already more uncertainty. And this metric should be learned from the data. I will talk a bit more about this later. Okay, and then D5 is just if we assume IID, noiseless data, then within the support of the training data points, there the uncertainty should vanish if we have more and more training data points. Okay, it's a little bit more details to D4. So learning this metric, a Gaussian process, for example, with a fixed kernel is not able to learn this metric. Like here, I have a 2-dimensional input, and these white dots correspond to my 16 training data points, and completely independent what the y value, what the output of this training data points is, the uncertainty always looks the same. It only depends on the x position of the training data points and on the kernel. While for our method, here in these 2 examples, we have that the right 8 points have an output of 1, and the left one has the output of -1, which is not shown in this plot. And here we only plot the uncertainty in this plot. And so our model should learn that the feature x1 is a very important feature, so a small deviation in x1 should strongly increase the uncertainty, while x2 has no influence on the output, so deviating a bit in x2 should lead to less uncertainty. And since neural tangent kernel and wide Bayesian neural networks, they both converge to Gaussian processes, they are also not able to benefit from this D4, while our method does. Okay, how does our method work? We have an architecture with 2 outputs. One explicitly models the mean, and the other one models the uncertainty. And then upper and lower uncertainty bound can be obtained by adding or subtracting the uncertainty to the mean. And then we have a loss function, which just in a very classical way fits the mean through the data. And we have an additional loss term, which promotes that the uncertainty is close to 0 at the training data points, and an additional loss term, which makes that the further we move away from the training data point, the larger the uncertainty gets. And then we have certain hyperparameters to tune this. Okay, in our experiments, where we have noiseless simulated data coming from a Bayesian neural network, so these other methods with approximate Bayesian neural networks should be optimal there, but we perform clearly better. And surprisingly, even in real-world noisy data sets, we perform similar good as other methods, while our method should be actually extended to deal with noise, but just our plain method, which does not deal with noise, also performs similarly well as other methods here. Okay, and then we study noiseless Bayesian optimization, where you have some expensive to evaluate function, and you're only interested in finding the point where this function is optimal, like maximal here in this case. And there, it's particularly important that the uncertainty really narrows down at the training data point. So such other constant thing, maybe in the previous metrics, this would be, wouldn't hurt so much, but for Bayesian optimization, then you would get stuck and always keep querying this left point, and the uncertainty wouldn't go down, while for a reasonable method here, the uncertainty is larger, so you should become more curious to also explore this to find this optimum. So, and we tested this with upper bound as acquisition function in the language of Bayesian optimization. We perform clearly better than the other benchmarks most of the time. Okay, and then this method can also be easily extended to monotonic functions, where we can also compute the upper uncertainty bound with a slight variation of NOMU, where we have the prior that our function is monotonically increasing. And this is quite a specific situation, because then we have 100% uncertainty bound, where we know the truth cannot be below this bound. This is also one reason why in this case Gaussian processes wouldn't work, because Gaussian processes always have it's always possible to be infinitely far in both directions. And we use this in an application in market design. Okay, and so the goal of this upper uncertainty bound is most of the time also for out of sample test training data points, this uncertainty bound should be above it. Okay, thank you for your attention. Yeah, so in Bayesian optimization, it's very straightforward. Then it's the in Bayesian optimization, it's the mean regret. So how good is the best? You try to optimize this optimization problem, and for optimizing optimization problem, so finding the point where the output is the highest. And then if one method just ends up with this point, then it has a certain height, and the higher you are on average, the better. So this is for regression. Here we use the negative log likelihood on the test data points. So if we have a posterior distribution, and for this posterior distribution we can compute a density, and then if it has the logarithm of the negative logarithm of the density should be high on average. And then it's not too wide or too narrow.
Thank you. Other questions after?